about the lessons learned from the Rockefeller Center UTEN project, entitled Developing a Utility-Owned Thermal Energy Network in New York City, Evolving Lessons Learned. I'm Charlie Marino, Senior Vice President at WSP, and I'm joined by Adam and Brittni. If you guys want to introduce yourselves.
Adam Shelly, Director of Innovation and Project Development at Ecosystem.
I'm Brittni Provencher, an Engineering Manager at Con Edison on the Utility-Owned Thermal Energy Networks team.
Right, terrific. So we'll get into a conversation today about lessons learned focused on recapping what the actual filing was like and some of those key takeaways, some of the major hurdles that we encountered as we closed out the project, such as how do we get across Avenue Americas, which we touched on before, and we'll circle back to that. And then lastly, talking about system sizing and future expansion. So Brittni, please take us away.
Will do. Hi, everyone. The reason why we're talking to you today is because of a law that was passed in New York in 2022 called the New Utility Thermal Energy Networks and Jobs Act, or UTENJA for short. It allows utilities to own, operate, and maintain thermal energy networks in their service territories. The law also required the 7 biggest utilities in the state to design and propose at least one thermal energy network pilot project to the New York State Public Service Commission, or the PSC for short. As a result of UTENJA, UTEN team was formed at Con Edison, and the team filed 100% CDs for 3 UTEN projects with our regulators. But the project that we're going to talk to you today is the Rockefeller Center project. But before we start, what is a UTEN? So a UTEN is just a district energy system, but one that's owned and operated by a utility. Most of the time, district energy systems go hand in hand with geothermal applications, but installing boreholes in large densities like New York City can be a challenge. So UTENs can use other heat sources and sinks than geothermal boreholes, like waste heat captured in condenser water in chilled water plants. So New York State implemented a phased approach to each utility's UTEN pilot projects. Con Ed completed stage 2, the engineering design phase, on July 9th of last year, when we submitted our stage 2 filings and construction-ready drawing packages to the PSC for our 3 projects. We're hoping that we'll learn that at least one of our projects will be approved by our regulators to head into the construction stage, or stage 3, soon or within the next few months. Once a project is approved to head to stage 3, it will take a few months for the procurement process and to enroll customers. We also think it'll take about 1.5 years to construct the project, so we're looking at a potential Q4 of 28 start date for our project to be operational. Since the pilots will run for at least 5 years, we think the pilot will be in operation from 2028 through at least 2033. As a result of UTENJA, Con Ed is creating a new thermal commodity. Since everything is new, Con Ed hired multiple companies and regularly engaged with the project stakeholders shown on this slide to design a safe, reliable, and efficient UTEN pilot project within a short time frame. Ecosystem and WSP designed Con Ed's Rock Center UTEN pilot project, but Con Ed also hired 2 peer reviewers, KWL and RCM, to ensure that the project was reviewed by industry experts before it was submitted to our regulators for approval. So Con Ed's Rock Center project captures waste heat from a large interconnected campus of buildings in Midtown Manhattan and distributes it to 3 large commercial office buildings by installing about 8,000 linear feet of piping. The 3 customer buildings will use modular water source heat pumps to convert a portion of their heating systems from steam to the UTEN. This UTEN is heating only, and it's an ultra-low temperature hot water system with the temperature in the utility-owned piping varying from 80 to 92 degrees Fahrenheit. Customer-owned heat pumps will boost the water to 130 degrees before it's distributed to a customer's heating zone. The system will only be operational from November through April, and when operational, it'll capture waste heat from the condenser water return in the large central chilled water plant. The waste heat captured in the plant comes from internal building loads in IT rooms throughout the campus. A new room will be constructed in the campus's shared loading dock to house Con Ed's Energy Center equipment needed to operate the system. It'll also house the water source heat pump that will produce the 130-degree hot water that will be distributed to two of the three customer buildings. In order to connect to the large customer building across 6th Avenue, 1221 Avenue of the Americas, we'll install pipe through the subway station that's located underneath 6th Avenue. But Adam will talk about why we decided to do that shortly. So when designing this project, Con Ed had several priorities in mind from a utility perspective. One of our biggest priorities was to generate as many learnings as we can for both Con Ed and the state. How easy will it be to retrofit existing buildings so we connect UTENs? And will UTENs help provide a more cost-effective way to help the state electrify? We won't have the answers to these questions until we finish constructing and operating one of our pilot projects. There are also other factors that influence design decisions, like compatibility with existing infrastructure. For the Rock Center project, since the perimeter induction unit loads for all three buildings already use hydronic heating, those loads were targeted to be converted from steam to the UTEN. So I'll now pass the presentation over to Adam to start talking more in depth about design details and the lessons learned while designing this project, particularly why we decided to install UTEN pipes within a subway station.
Yes, thanks, Brittany. Just as a quick reminder, this session is called Evolving Lessons Learned. And why is it an evolving lesson? Because we were here last year discussing this exact thing, the 6th Avenue crossing. Obviously, in Midtown Manhattan, we had concerns about the viability, but we were confident that we could do a crossing on 6th Avenue. Just to give everyone a reminder of this location, it's about a block away from the Rockefeller Center Christmas tree, an ice skating rink. So it's a very densely occupied area. So our first goal was, how do we cross 6th Avenue to connect these other buildings? We attempted to trench. Next slide, Brittany. In order to do some test pits and see what was really under those roads, because there's a ton of different maps and plans of the New York City streets, but none of them are 100% accurate. Each one of these colored lines represents a different path in which we thought we could get this piping, and we intended to explore them all by digging test pits, as you can see in the red shapes with the different numbers. So we originally planned on doing 7 different test pits. Over the course of this investigation, we started with 1, continued with 2 and 3, we determined that doing 7 and 6 were not necessary because 1, 2, 3, 4, and 5 all proved to have unfavorable results. And by unfavorable, I mean it was impossible to cost effectively get a pipe across the street here. Our goal is to obviously pilot these thermal energy networks, but we want to do it cost effectively. We essentially want to make those U10s U9s because we want to cut the cost. Obviously, that was an extremely funny joke, but this path could not happen. So where do we go from here? Very early on, Brittany, Charlie, and I decided that there were 2 ways to get a pipe across 6th Avenue. One was in the street, and the other was in the subway. Next slide, Brittany. These are a few of the pictures just proving out that the pathway across 6th Avenue was not viable. Each one of these pipes had significant impact on building operations if it were need to be severed or moved, in addition to being extremely expensive. It's expensive to change location for utilities anywhere, but especially in Manhattan. So here's the subway that's right below 6th Avenue that connects a number of different buildings in the area. This is the upper level, just below is where the trains are, and our goal is to get from one side of the station to the other. There's a lot of different constraints, whether it's overhead, ADA, thermal, safety. All of these need to be considered during the construction and then also the maintaining the pipes there. One interesting point, which boiled all the way into the tariff development, is you have to lease MTA space, and that's basically by the cubic foot, not by the square foot. So all of the different dimensions really mattered here. Next slide. So what we decided to do is sneak in through the Rockefeller Center buildings on the right and hug a wall going left, and then break it apart into a different manifold so that we took as little headspace as possible and we can meet all of the different clearances. It is very, very tight, down to the inch. One thing that we do like about it is that we hope people know that there's a thermal energy network around. So that's an exciting marketing opportunity that we hope gets taken advantage of by the NTA and the other stakeholders. Next slide. We did a lot of 3D visualization. We hired a scanning team to do a cloud point map of the entire station, so we knew exactly where the valves were going, exactly how much insulation would take up, if there was any additional materials like wall coverings that the MTA required in order to maintain their standards, because not only are we maintaining Con Ed's utility standards, but we're maintaining the MTA's standards, we're maintaining Rockefeller Center standards, Tishman Speyer standards, Rock Group standards. So this is designed to meet all of those requirements. So it breaks up into 8 different runs, I believe, going across, and then manifolds back together on the other side. Next slide. Here's another view of that, the 3D models showing all of the different connections. I'm sure it'll look just as beautiful as everything else in these subway stations when it's finished. And one more slide. So the lesson learned here is, as long as you're prepared and thinking about everything that can go wrong at the beginning, there could be a lot of different options. There was the potential for the street crossing to make this project not viable and kill the project there. We were well prepared. We thought that this was very much a second tier option for us, but the more we continued to explore it, we realized that it was actually more cost effective and it was potentially more scalable. The New York City is a vast network of really large, powerful connections in some of the city's most dense neighborhoods. If you can extend these systems throughout the subway and mimic that, there's a lot of potential for expandability, which Charlie will get into as part of his slides. Charlie, take it away.
Thank you, Adam. So now talking a little bit about lessons learned associated with system sizing and scheduling. I'll walk you through a few different key components, starting with evaluating the heat capacity that we were looking to recover from the central plants and understanding essentially what was the foundation of the low and highs of what the actual output could be. So the baseload heat rejection during the winter months overnight is approximately 17,000 MBH, while the weekday averages would range between 23,000 and 31,000, depending upon the month. And the way we analyzed this was evaluating BMS BTU meter data that was provided by Tishman Speyer, great collaborative stakeholder on this project, as well as developing our own energy models to look at 8760 information and calibrating that info. So what you see here is an output of specifically looking at the condensed water heat rejection and overmapping that with, we're looking at the winter specifically. This is a heating only UTEN, which is an interesting aspect of the project, and understanding how it would provide heat during different types of outdoor air conditions. And so on the next slide, we have a heat map here, which helps illustrate the heat rejection loads across average hourly weekdays and weekends, and reveals that the peak heat rejection during the winter occurs between 6 and 5 p.m. You can see that where those orange areas are, and this occurs essentially a little bit differently on the weekends from 9 to 5. So this follows the typical operation of a commercial office building complex. Again, this is a campus, but predominantly commercial office space. And so we needed to keep this in mind when understanding having the availability of UTEN heat all heating season long, and how that would react with the different customers. And so once we have a good sense of the thermal source sizing, we then take this information with the next slide. You can see we're starting to give some consideration to Now, what do we actually need to give for the customers and their demands that we have, which is represented with that red line there. We developed additional EQS energy models for all of the buildings, which were calibrated and dialing in our understanding of all of their heating systems, and especially those that are connected directly to the UTEN system. And we tried to understand if we would have enough availability for those systems. And as part of our project, we had to understand also from a resiliency perspective, what would we do if we can't meet those hours? So you can see here, essentially like 99% of the time, we are in good shape for covering all of the heating systems connected to the UTEN system. And by that, I mean, there are still some systems within the customer buildings that are not connected, those that are still on low pressure steam directly with steam coils and air handling units that will transition over time as they phase out those systems. And we'll talk a little bit more about that later on. But for here, you know, we're very close, but we still care about that 1%. I'm going to talk a little bit more about that in the following slide. So you can see here, you know, when we dig in a little bit further, we have a lot of capacity at the central plant, and that's represented in the top left graph there. You can see we have a lot of condensed water heat, but the actual total UTEN heating load is a bit lower than that. And part of that is because we're not leveraging all of the heat rejection during this pilot project. There's concepts in place for future expansion where we could utilize all the heat being developed from the plant. But for that reason, we're not meeting all of those hours. And, you know, as we essentially move off of weekend mode into weekday mode during the winter, and there's a typical spike that occurs within most commercial office buildings in New York City for Monday morning warm-up cycles. There are hours there where our system has a bit of a shortfall of trying to provide all that heat for those connected systems, and that's represented on the right side graph. You can see those gray areas where we're having a dip in the UTEN available heat compared to the available heat, which is presented in that dash blue area graph there. And so for that reason, our systems are still connected to the Edison steam distribution system. It's actually connected in series so that if we're starting to have some low running hours, the rest of the heating capacity can be made up by the Con-Ed steam system, which is really fantastic. And for all of the UTEN systems as part of this pilot, there had to be a way to demonstrate how we're covering those unmet hours. And so we're still utilizing steam as that source. And so, you know, when thinking about that, moving to the next slide, and having conversations with, well, what can we do with that potential heat at the plant and expanding in the future? We wanted to walk through some of that with you today, sharing some of this for the first time, really in a public forum. But there's a lot of ideas about how to not just create a pilot project that doesn't expand, but give notion to how these can move forward. And you can see here, there's a number of concentric circles kind of overlapping. This system isn't designed to ever expand that loop size that we have and just connecting all the buildings in the future. Likely we'll have additional networks that both have their own customers as well as their own heating sources that can tie into one another and share as redundancy factors. But these are some of the loops that we've given some thought to in this direct area. You can see the pilot area that we kind of walked through before, and the post-pilot expansion, which is a couple of additional buildings on the west side of Avenue Americas that have future connection caps that we can expand further north within that same concourse area, so we don't have to worry about going into the street and bringing on some of those loads, although limited. On the right side, to leverage even more heat capacity from that chilled water plant, you know, there'll have to probably be another energy center and expansion there. And there's interest there, and it might not necessarily even be a Con-Ed owned project. There's other frameworks in place that might give some consideration if it's a municipality system or private ownership system. That'll be interesting to see how that would come together over the years. And then lastly, trying to get more diversity in the system with a very large hotel in the area. That would likely have like its own unique profiles and set of obstacles to overcome. But this is the way we would probably expand to avoid additional conflicts trying to cross over to Avenue Americas. And then, so Brittni, back to you to take us home.
Thanks, Charlie. So now that we've shared some details about our project, I wanted to touch on some things we've learned from designing the Rock Center UTEN that can be applied to other TENs. So while working with the central plant's operations team to generate utility-grade waste heat and minimize central plant impacts, it was agreed that its sequence of operations can be changed to prioritize the use of larger, different chillers during all heating hours. These larger chillers are currently used during high winter loads. This change was more palatable to the operations team than installing a new heat recovery chiller in the central plant, which would have required relocating existing equipment, retrofitting plant piping distribution, and modified controls. We didn't start designing the project with this change in mind, so it's useful to know this can be an option while modeling future UTENs. Although hot water systems typically don't utilize ultra-low temperature designs, it made sense for the Rock Center UTEN due to space limitations to install a new machine in the central plant, which would produce higher temperature condenser water return. The ultra-low temperature operating range can also allow additional heat rejection from other nearby sources if the Rock Center UTEN is ever expanded in the future. This design opens up avenues for UTENs in areas that are otherwise constrained and couldn't implement a traditional hot water TEN. It makes sense that operating a heating TEN could potentially only make sense financially during the heating season, but we didn't start designing our project with the seasonal operational approach in mind. This approach is one potential solution to making future heating-only TENs more cost-effective for utilities and their potential customers. Now, since the Rock Center UTEN is a pilot, we anticipate future UTENs being cheaper to implement. We had to create a brand new commodity since we've never done this before. So if Con Edison chooses to design another UTEN, costs will go down, specifically for the SCADA and IT systems that will already exist if we construct one of our existing projects. We'd also require fewer design review iterations in the future since we'll know the types of information to expect after designing 3 UTENs. Now, as far as the future of UTENs, Con Edison sees them as being a potential load relief tool to manage the electric grid. As existing buildings electrify heating, implementing a UTEN may reduce the distribution upgrades that would be required to support additional electric demand. Constructing a UTEN could potentially be cheaper in an area that otherwise would have required a new substation or electric infrastructure upgrades. UTEN's offsetting costs to upgrading the electric network could provide a true business case to develop more TENs in the far future. So if you're interested in more information about Con Edison's UTENs, visit our website using a QR code on the slide. It has a link to our Rock Center Stage 2 filing if you're in the mood for some light reading of about 160 pages about our project. Thank you for your attention. If you have any questions, feel free to contact any of us using the email addresses you see below. Thank you.
Thanks for joining us. Enjoy the conference.
Take care.